This episode of Gauging Quality is sponsored by PQ Systems, developer of GaugePack, the original gauge and calibration management solution. For more information, visit pqsystems.com.
Welcome to Gauging Quality, a show about gauges, gauging, and gauge calibration, sponsored today by PQ Systems. I'm your host, Dirk Ducharme, Editor-in-Chief of Quality Digest.
And I'm Craig Howell, President of CPM Labs in Rancho Cordova.
And today's show is going to be a little bit different than what we've done in the past. If you've watched this before, normally Craig comes on with a piece of equipment and we talk about that particular gauge and how it's calibrated, kind of the care and feeding, and so forth. So there's a little bit more equipment on the show. Today, we're actually going to talk about something a little bit more important, perhaps, kind of what happens after calibration, and that is the calibration certificate.
The calibration certificate. We're going to cover what you should look for in a calibration cert, what your auditor is going to look for in the same thing, and what's required and what is just good practice, and even some suggestions.
Exactly. And we're also going to take some questions from you, the viewers. We have some questions that have already come to us that we want to address. Also, if you have any questions anytime during the show, go ahead and send them to us. You can send them to techno-live@qualitydigest.com, and we will get them onto the air. We're actually going to start off with a question that we got just, I think it was just a few weeks ago. And this one had to do with kind of a really inexpensive gauge. Why don't you tell us about that?
It's a screw pitch gauge. They look like a set of feeler gauges, only instead of being thickness measurement, they're sawtooth. They are actually different pitches of threads. I think we have a picture of one up right now, and it'll show what the different leaves look like. Each one has a different quantity of teeth on it, and that relates to a pitch. 32 pitch, 40 pitch, 80 pitch. You visually hold these up against the threads you're trying to figure out what the pitch is until the teeth mesh with the right size thread, you'll know the pitch.
And I guess the question on this was, can you actually calibrate this? Now this thing costs like what, $6?
It costs $6 to buy and $7 to ship, and it would be about $300 to calibrate the whole thing. So it's cost prohibitive, but let's answer the viewer's question. He said, how do you calibrate it? And that might be the tool he's using to accept the product. And the ISO specifications say if you're going to accept a product, that tool has to be calibrated. So he has to calibrate that tool.
Okay.
I would suggest they might say there's a certain pitch that this thread they're manufacturing should be. Hold up the thread gauge and make sure the pitches match. So we're going to calibrate the thread, the leaf he's looking for, and one a little bit finer and one a little bit coarser. And this way he can hold up the wrong ones and make sure they do not fit.
Okay. And how would he actually do that calibration?
How you would calibrate it if you were to do that sort of thing, probably the tool you would use is an optical comparator. You'd be looking at the shadow of it. I'd suggest an overlay of the angle. He asked for a 55-degree Whitworth thread. There's also 60-degree. There's different threads that you have an overlay shown for the different angle to make sure that it meets the 55-degree angle. Then the next thing would be the actual pitch. You would count over a distance, usually 1 inch. You divide 1 by the pitch, and that's the spacing. Let's say a 20 pitch. I believe the spacing is 50 thousandths between teeth. You'd find a point on one of them on the comparator, zero it, move over, go 1 inch, make sure you had 20 teeth.
And measure the angle as well.
And the angle.
So I mean, does this qualify as a calibration? I mean, verification, I guess, or is that the same thing?
It's more of an observation. It's verifying. It's more of a validation. You're validating that gauge is going to get you the answer that you need in order to use it on a traceable type of product.
Okay. Is there any kind of a plus or minus that you would put, like you mentioned using a template to make sure that the angle is correct. Would you specify that it needs to be between 59.5 and 60 point? I mean, you know what I'm saying? Is what kind of if you're going to do it this way and you're going to quote calibrate this thing, I mean, do you need to make any kind of specification for it based on your own needs?
You have to have what would constitute a failure,
okay,
and what would constitute accept. How you get there is all in the details. The manufacturer does not have a specification for it. You would have to make a procedure for it. A good process you could use would be the machinist handbook. It has thread specifications. You could use their angles for the lowest grade hardware store type of bolt.
Right.
and use those. And just as long as it's acceptable between you and your customer, and it's written and documented, yes, you could do that.
Okay.
So I would check the three different leaves on the comparator, get the specs out of the machinist handbook, and verify and keep record of if it made it. Again, can we go to the overhead camera? I've drawn a little
Sure, a little gauge cam. Okay.
gauge cam. This one in the middle is when it matches. You hold the gauge up to the thread, and each different leaf goes right down the middle. It matches perfectly.
So we got the thread we're measuring on the bottom,
Right.
and this is your, on top,
This is the
your
template.
The template, okay, yeah.
If the pitch was too fine, that's the top. You'll see these teeth don't fit down into the thread you're looking at. Or the opposite situation, if the thread was too coarse, instead of fitting right down in, it would not quite get in the hole.
Okay. All right.
So that's how you could tell, say this was the 30 pitch, this was maybe a 32, and this was maybe a 28.
So that's basically how they're using them.
Correct.
Okay,
They just
all right.
hold it up. It's a visual aid.
Okay.
That's why the whole question of calibration would throw you back, but I understand. Sometimes they have to do that.
Yeah, if that's what you're using to okay your equipment, then you've got
You
yeah,
have
okay.
to do that.
All right. So we're going to get into the kind of the main meat of our show today, which is calibration certificates. Again, if you have any questions, send them to us at techno-live@qualitydigest.com.
All right, what should you look for in a calibration cert? You've sent your tools out for calibration and they come back. The certs look quite different from different calibration labs, so what's the criteria? What's required? So going to the ISO specs, there's a series that's about 6 different topics that are required in there. You do have to have a unique identifier. We use a number, we call it a file number, that identifies that tool to that cert, and it can't be mixed up with any other tool. You know, because that is the number assigned on the cert, and that's the number on the calibration tag. You know that cert goes for that tool. There are different identifiers. A lot of companies have their own system there, where they will have a number. We will include that on the cert, but we always use our own because different customers have different. They might have a new management come in and want to change everything. We'd lose the traceability.
Okay.
So unique identifier.
Which might be a serial number, or it might be something.
It could be the serial number. We do that on a lot of electronic equipment. We use the factory serial number because that'll never change. It'll never duplicate.
Or it could
as long
be
as
just
it's long enough.
Or it could be a permanent sticker that has something unique to that particular
Something
device.
unique to that tool that ties it in. The manufacturer and the model and the serial number, if one's available for that tool, also should be shown. Some tools do not have serial numbers. Some of the micrometers, calipers, they won't have a serial number on them, so we'll put whatever we can find on it. You can always find the manufacturer and model. That's always available. That should be on your calibration cert. You should look for that. Auditors will be looking for that. Very important part is the traceability statement. You have to have a statement on there that the standards used to calibrate this are traceable back to, it's usually international units or SI. And a lot of those are based on physical constants. There's a lot of different ways they base what the standard is, but you have to the cert has to have a statement that all the standards are traceable to that.
Okay, and in our case also they're traced back to a physical lab like NIST,
Like
for instance,
NIST
in the United
US,
States. Okay.
Germany has one, Switzerland has one. There are quite a few different ones, but they do have to have a traceability statement.
So this means that it's just going back to
An unbroken link.
all the way back to the original. Well, not the
Constant.
original, but yeah, to the constant, right? Exactly.
The link to the Pharaohs.
Right. Yeah.
We'll go there. Another part that needs to be on each calibration cert is who calibrated it. We don't calibrate everything, and we don't claim to calibrate everything made under the sun. I'd suggest if somebody claims they calibrate everything, you might question, are they calibrating anything? So who did the actual calibration? We identify it with our initials. If it's sent to a third party, we will refer to the third party, the manufacturer, or
So you mean
whoever.
if a company sends something to you to be calibrated, you might calibrate it if you have that capability,
Yes.
or as a calibration lab, you might send it off to another calibration lab that
Correct.
might have the capability that you do. So you work as kind of a middleman or a
As
broker
a
in some
team.
cases. Okay.
Correct.
All right.
And what we will do is we will take their calibration cert and we'll put a cover sheet on it with ours, because all our information is in the same place on each cert. In an audit, you want things as easy to find as possible. So we keep everything in the same place, but you have to identify who did the actual calibration. There should be no question.
Okay.
So then the next step would be, what procedure was it calibrated to? It has to identify a procedure, whether that be a military procedure, a manufacturer's procedure. Sometimes a procedure doesn't exist. You have to have an agreed upon one with the customer, and that can get pretty in depth. If you're doing medical device, some aerospace, it might require validating that the procedure you're using is actually objectively achieving what you're after.
Actually, a good example of that, something is the question you just answered. There doesn't actually exist an official calibration procedure for a pitch gauge, but you come up with one, and as long as you've documented and that you can prove that it does what it's intended to do.
And your customer is in the loop and agrees with it.
Okay.
We do that a lot. There's equipment that is obsolete, no longer being manufactured. The manufacturer's gone out of business, and there are no specifications. So we'll always turn to, are there any other published acceptable specifications, military documents? A lot of the aerospace companies have huge databases because they deal with this. They have to calibrate everything. So if none exists, yes, we might make one. As long as it's documented and everyone's in the loop, and that's also going to be part of one of our next viewer questions. As long as everybody is in agreement, you can do that.
Okay.
So that would be the procedure. The last part is the results. What was the result of the calibration? The typical ones would be accept, reject. Sometimes there will be limited calibration. A multimeter might have a lot of functions, and one of them is not within spec, but you don't use that. So there would be a limited specification, not calibrated for resistance, not calibrated for whatever the case. And there is also a situation where you'll remark things such as a micrometer standard, a cylindrical ring gauge. There is no adjustment. They are what they are. And sometimes what they are is out of spec, but it's perfectly usable to the customer. All other parameters were met, just the length has changed or the diameter has changed due to the metals. So we will remark them to what would be acceptable within that specification.
So instead of a 1 inch standard, it's a
0.9999.
Okay, yeah.
Correct.
Okay.
So those are what is actually required. Those have to be on the calibration cert. As always, the devil's in the detail, and the detail level is what will separate a good calibration cert from just an adequate one, a marginal one. Some details you have to have. Data is always a question. Does it show data? Does it not show data? Some of the multimeters would be 18 pages long worth of data. We don't typically provide that unless, and we have to provide it, if an adjustment was made, or if an out of tolerance condition existed, or if we do have to remark a size. You have to show the data because the customer, the customer, may need the information to see what have you been accepting with this gauge. Is it significantly out, or is it just academic? Plus or minus 5 thousandths and it's out 5.5. It's not legal. It has to be documented as out of tolerance, but your engineering may say, we've designed that in, that's not a problem. Plus or minus 5 thousandths, it's out 30 thousandths, that's significant. You may end up, I'll give another example, would be a wire crimper we did the other day where Underwriter Labs has a pull test. The conductor has to not pull out before a certain force. Say the force was 20 pounds, it pulled out at 3. That's significant. They need to know what was manufactured with that crimper and take a look at the wires that they crimped with and see if they have to redo it. Okay. So data is always needed when it's out of tolerance. You need to know how far out and which direction. That can make a big difference too. Or if we did an adjustment, a lot of times we will accept with adjustment. It's allowed plus or minus 5, and it's going to be out there for a year, and it's running 4.5, 4 and 3. It's almost 5 thousandths. A lot of times the customer will have us put it back to a nominal. We do have to record the before and the after data. That needs to be recorded.
Now that's typically what I think of as calibration.
But that's not always. Sometimes that's called re-zeroing or aligning.
Okay.
It's not. Some it is required. I think one of the electronic manufacturers says in order to meet our yearly suggested spec, these should be readjusted each time. So we would do that sort of thing, but it has to be documented.
Okay.
So the detail level, another part is traceability. Now I was looking through all the specs because I was going to say you have to show your standards on the calibration cert. That's required. You have to show it. I may be wrong there.
Okay.
The wording, the actual wording is you have to have evidence of traceability. I take that to be a listing of the calibration standards. If I've listed them, I've given evidence of the traceability. It's rather than just saying the part's good, we certify, it's all good, honest. I've actually told you what did I use, when is it due for recalibration, that sort of thing.
Oh, you mean your standard?
My
like
standards.
Your gauge blocks, for
My
instance.
gauge blocks,
Okay.
that sort of thing.
Okay, and we know that your gauge blocks from CPM Labs are traceable to, okay, gotcha.
So there we provided, that's where I get back to, we have to show those. I would suggest any cert's going to show that. Any good, competent calibration lab is going to be showing the standards that they used. An auditor could easily question if they don't, where's your evidence? And I can see how you could get around it, but that would just be a much better method is to show. We always have shown the actual standards, and we always will.
Okay.
So that might come more under best practices than required, but you do have to have evidence, so we're going to show the standards.
Okay.
So the interval would be another question. The interval, we are not allowed to assign the interval. Calibration labs cannot.
And we mean the calibration interval. How often
interval.
between?
Should it be a 6-month interval? Is it due for recalibration in 6 months, 3 months, a year? Whatever the interval is, we're not allowed to assign that. You can figure why we'd say we should be out there probably every day or every week. On the other side of the coin, if some people think, well, a 1-year interval is fine, let's go with 10 years. That's not an appropriate interval either in most cases.
Now, doesn't the manufacturer of a micrometer or caliper or whatever the tool is, don't they normally say what the interval should be?
A lot of them will. It's almost a blanket statement. They don't know if you're going to use that tool once a month and put it on the shelf, or if it's on a production line. I was doing a production line yesterday where a scale was getting near to out. They opted to pull it. Where something is going 24 hours a day, 7 days a week, it never stops. That's going to obviously have a shorter interval than something that's used once a month and put back on the shelf in a very clean environment. The manufacturers will have a suggestion a lot of times. A lot of times they can be called to find out what might be inappropriate, and they're going to say it depends. What does it depend on? It depends on the stability of the tool. Is it stable? A micrometer standard is stable. It doesn't have a lot of moving parts to it. Something very, very sophisticated and technical might have a lot of parts. That might not be as stable an instrument. It might have a shorter interval.
Okay.
So stability, usage, the 24/7 versus once a month. The environment it's used in. Is it used in a laboratory environment? Temperature. Temperature has a lot of effect on these gauges, especially the mechanical ones. And just storing it in a bad temperature, we'll find we get out of tolerance or near out of tolerance conditions more often than the same exact gauge used the same exact way in a lab, just because of stability.
So the temperature, wide temperature fluctuations. Okay.
It could be particulate in the air. If it's used in a dusty environment, that's obviously going to degrade the tool. So those are some of the factors to establish the interval. An auditor will always ask, how did you establish the interval? And you have to have the right answer, which you should establish it. You can use your calibration certs for the history. I believe our sponsor has something in their software where you can look over previous calibrations and see how did it perform.
Okay.
And that could be a basis for either extending it slightly or decreasing it. Every time if it comes in it needs adjustment, your interval's too long.
All right.
You might be buying product with it when it was out.
Yes. Oh, I see. So if every time you're saying if every time you do a calibration, it needs some tweaking, you're probably at the long end of your interval.
End.
Ideally you wouldn't want to have to see any tweaking.
Right. A lot of customers, their policy is they want to get the most out of their calibration. Understandable.
Sure.
It's an overhead cost. They'll want to catch it before it becomes a problem.
But
So
not
as
too
long-
early.
Not every day, not every
Right, right.
week, but they want to see as received intolerance and as left intolerance every time. When it becomes out of tolerance, now there are problems. And auditors, a lot of times, this isn't, again, required in the calibration cert, but a lot of times in an audit, an auditor will say, let me see some examples of some out of tolerance certs you've gotten back. They will be wanting to see, do you have a procedure in place to address that? some of the considerations. Is it academically out of tolerance, or is it significant? And if it's significant, that's what they're going to hone in on. What did you do? Once it's out of tolerance, what did you do about that? Do you have a process in place to cover that?
I imagine also if it's out of tolerance, I'm guessing they also want to know if you have a history of what product was measured with that tool while, up to that point. Because if it's out of tolerance, you may have measured product with it while it was out of tolerance, and I'm guessing they would want you to know
what was done with it.
What was done with it, yeah, exactly.
Right, and a lot of different companies we work with, they will have to list the tool down on their work process forms of what tool they use to check what product. Again, it gets back to how significant was the out of tolerance.
Right.
If it was just very, very slightly, that might not be as much of a concern as if it's like the wire crimpers that pulled out is 3 pounds.
Yeah.
So yes, they would want to see that, and you'd want to have control of that. These are just good things in your audit prep. And again, GaugePack has an excellent way to look back on these and see how's it holding up, so you can adjust the interval appropriately.
Right. Okay.
So the interval adjustment is something that the customer defines, not the calibration lab. We've covered significant out of tolerance, and that's something that's always asked about in an audit. How do you cover that? What do you do when that situation arises? So that would be one good practice is how long does the calibration lab store your calibration certs? We do a calibration, we hand you, the customer, the cert. We always keep a copy and we store it, and we define our quality manual how long we store it. Some customers like Boeing, they have requirements that the calibration cert must be available for so many years, even after the product is out of use. I've seen some that say 5 years, 7 years after the product is no longer in use.
Now, why is this requirement on the calibration lab as opposed, because to the customer, the customer's getting a copy of
the requirement's on the customer, not on the calibration lab.
Okay.
But a lot of customers will require us as a condition of doing business with us. How long do you keep your certs? It's a great question to ask a calibration lab you're considering. How long do they keep the certs?
Okay, so in case, I guess it's kind of a form of backup in a way.
It is a backup.
Well, we always know we can go back to the calibration lab and they're going to have a copy as well.
Right.
Yeah, okay.
Now, speaking of backup, you get a third-party cert. You send something to CPM Labs, and we don't do it. We send it to the manufacturer. They give us a cert. We put our cover sheet on the cert, and we give it to the customer. Question to ask, is the calibration lab keeping a copy of that in case you lose your only copy? You may be able to go back to the manufacturer, but even that can sometimes not happen. We make a good standard practice that we scan a copy of the manufacturer, the third-party calibration cert. Great question to ask the calibration lab you're considering. Do they keep a backup copy of what they just gave you? Sometimes records get misplaced by the customer, especially just before an audit, always just before an audit. It's great to have that backup where you can call and say, the parts we sent back to stare at, do you have the calibration cert? And our answer is going to be yes. It'd be a great question to ask.
Okay.
So who stores that? There are some differences in how the cert will physically look on an ISO, a full-up ISO cert compared to a commercial calibration lab cert. The full-up ISO cert is always going to list the uncertainty of measurement. That's absolutely required.
And the uncertainty of measurement is what? I mean, kind of.
Let's put it into a one-word definition I learned the other day that I really liked: doubt. It was doubt. It's not guaranteed it's going to be what it is. It's our tolerance. How uncertain are we of the measurement that we just provided you? We say it's 1 inch. We might bring that out 4 or 5 decimals, possibly 6 decimals. How certain are we of that number we reported to you? And that goes by the tolerance on our standards, our environmental tolerance, everything. The operator using it, everything comes into play on uncertainty. Sometimes the uncertainty can be scary when you see the uncertainty. It may appear to be the same as the tolerance. But remember, this is just doubt. This isn't a guarantee.
And this is worse, and uncertainty of measurement is worst case.
It's worst case of everything.
If everything aligns to the negative,
right.
your worst operator, your your worst equipment, the worst temperature spec in your room. I mean, it's everything, right?
It's everything combined.
Okay. Yeah.
But uncertainty of measurements required on all full-up ISO certs. A lot of the third-party accreditors have a stamp that they want you to use on the cert when you're doing these, and they state right on their website, no uncertainty, no stamp.
Okay.
They won't allow that. And it is defined in all the ISO programs. It says you must, anytime you report, I think they call it a numerand, anytime you report something, you need to have an uncertainty associated.
And even if it isn't required, it's just a regular commercial cert, still a good idea?
It's a good idea. It's not required. Some labs hold it to a ratio. They'll call it a TUV, total uncertainty value, or a ratio. 4:1 was the old standard back in the old aerospace days, 20, 30 years ago, back when I was working in that was what we kept, 4:1. Our standards are 4 times more accurate than the tolerance we're reporting.
Okay.
And that was a good practice. They've refined it some.
Okay.
So that would be some of the differences. One other thing you might want to consider when you're considering a calibration lab, especially for an audit, does the calibration lab have a quality manual? Surely you have a quality manual, but does the calibration lab have a quality manual? If you have that along with your certifications when an auditor is there, you're going to be miles ahead. They know you've done your homework. They know you've thought about this, you've read the manual, and you know that calibration lab's the right one. So not required, not part of the actual calibration cert, but quality manual would be an excellent thing to also consider.
And by something occurs to me, the new ISO 9001:2015 focuses a lot on risk and kind of risk-based thinking. A lot of things that seems to me that you're talking about is a lot of what you're talking about is kind of good practice. This all goes down to the more you understand about the process, the less risk that you're taking in using this calibration lab or whatever. You're kind of starting to minimize your risk the more you understand about their own process. So, I
agree with that.
And this documentation actually helps to show that you're taking these into consideration. You're looking at measurement uncertainty. You're kind of spot checking that your calibration lab has its own quality manual. The auditor probably is not going to ask, I don't think, whether your calibration lab has a quality manual, but if you can say, look, we have vetted our calibration lab and we like their processes because we've looked at them, that is just another, I think, in my mind, a feather in your cap that you've done due diligence in terms of assessing the risk of using a particular lab.
It's about risk and it's about objective evidence, and you're covering both.
Yep.
Which that is how the ISO standards are progressing. I'm really liking that. That makes sense. What makes sense? What's the risk and what's the objective evidence that proves you're doing that?
Right.
We could go to some viewer questions. We have another one.
That's true. We do have some more questions. These were sent in the last couple weeks, I think.
Right.
One of them has to do with a really interesting one, actually. Has to do with a tensiometer. This was an Instron instrument, I believe.
Correct.
Why don't we throw that question up? We have a 1,000-pound load cell in an Instron gauge. The manufacturer certifies it from 20 to 1,000 pounds. We need to use it in the 7 to 20 pound range. May I write a procedure to do that? Let me say that. So what they're saying is that the manufacturer spec is from 20 to 1,000, but he's using it at not just the lower range, but actually below the lower range.
Below the lower
and he
range.
wants to know, is that cool, and can he validate and write a procedure for that?
That is a situation that happens so commonly. It's actually addressed in a lot of the ISO standards. They will have what is the manufacturer's requirement of a tool, and then under it they will have special customer requirements. In my world, they call it special customer metrological requirements. Usually it's taking the tolerance and tightening it up. Maybe it's taking the tolerance and loosening it. They say we don't need it to be within that range, and ours isn't within that range, and our requirement, we can show that will work great for our product. Instead of talking about accuracy, this viewer is moving it to range. Any tool's designed to work within its range. Let's say it goes from 0 to 1,000, and the manufacturer knows it works best between 20 and 1,000. That's not to say it doesn't work below. It's just there are other issues that come into play, much more numerous than we're going to know. They're the manufacturers, they know.
And some of it, I mean, I'm not saying it's the case with Instron, but sometimes it's linearity.
Yes.
Is they want kind of the best spec that they can show is if you use it from here to here.
Right.
And if they start going below that, then they have to widen their specification, which doesn't look as nice.
Right.
So we're just going to limit it. We're going to say 20 to 1,000, and
you'll
here's your
never have a
accuracy.
problem.
Yeah, and then that way we can have a really nice accuracy spec where we may lose some of that accuracy. And again, I'm not saying this is true for Instron, but for some equipment, if you start going outside that range, even though you're capable of doing it, it won't look as nice on the spec sheet.
There's that. We see that a lot in pressure gauges, in torque wrenches. They're designed to be used mid-range. You know, a lot of the torque wrenches nowadays, they might go from 0 to 100 pounds, but they actually quit numbering it below that 20% range that they want you to stay within. It will still physically lock in, but they don't want you using it outside of that range. So how do we deal with this? And the viewer that wrote this in has done his homework. I've followed his different emails, and we've corresponded back and forth. What would you do? First thing you would do is you'd have to write a process to cover the range and how you're going to validate and make sure this actually works. Then you're going to have to document it and do repeated tests. You're going to have to make sure your quality manual allows you, the customer, to perform non-standard tests. Not uncommon, very common. There's always special applications they have to do, but what does your quality manual say you have to do? So that has to be covered. Always a call to the manufacturer is appropriate. They're going to say use a different load cell, but let's say this is the load cell that you have and it's working fine from your test. Is this valid?
So what did he do?
Okay, what he did was great. He first took the manufacturer's cert because they specify it from 20 to 1,000. And the manufacturer's cert showed data, value is showing data on the calibration cert.
Right.
They showed data for 20, they also showed it for a little lower. They showed it for 12.
Is that on that cert that we had?
I believe it is.
Can you give up that cert again, Chris? That calibration certificate? Yeah, there we go.
Yeah, I think the
we can't
first,
really see
first
it,
one is 12. You're going to have to trust us on this.
Yeah, it's 12.
It's 12 and then 20 is the second one. He's using between 7 and 20.
Okay.
So they've actually defined how is it responding at 12, how's it responding at 20.
Okay.
So what I would suggest he would do would be take and do a measurement below the range. He's looking to start at 7, so possibly check it at 6. Do a 3-point check at least 3-point check, low, mid, and high of the range he's proposing to work within.
And that's what he did, right?
And that's what he did. He did a number of tests at 5 pounds, 6 pounds, 7 pounds, and he documented them out. I think that he did a series of them, so he's also showing repeatability on his own form, and not
not this one. Yeah,
not on this one. On his own form, we don't have a picture of that.
Okay.
But he did a repetition at 5 and at 6 and at 7, and he used calibrated weights. He checked them on a calibrated scale. He did his homework right. He documented it, ran it by his processes, made sure it was valid, and he showed, if you take what tolerance the manufacturer would allow at that, they don't specify it there, but use their numbers. Say it's percentage of reading. It's got to be accurate within 0.025% of the reading, whatever. If you apply it to those numbers, you'll get a tolerance. Not the manufacturer's tolerance, this is the one for your special use. He was showing like a quarter of the tolerance was used over and over, repeated within 1 digit.
So what he basically did is he validated that this instrument would work within the range that he needed, and he checked it at every which way from Sunday and using traceable weights,
written procedure.
Yeah. So if an auditor comes in and wants to know, hey, how come or how can you use this outside the range of the instrument, he can show them documentation and basically show how he has validated what he's doing.
Right, so the documentation, that's part of the step, making sure his quality processes allow him to work in non-standard forms. Make sure everyone on his company is on board with it. Very important would be the customer that's buying the product. Yep. Are they aware of this? That here's what we're doing, here's our results. If everybody is signed on, I would say his process is valid. He was very complete in his data and in his methodology.
Okay.
So that seemed like a great response from him.
Okay. Was that it on that question?
That was it for that.
Okay, great. We'll get to another question here. Just remember, if you got any questions right now, send them to us at Techno-Live, I know where we're at, Techno-Live at qualitydigest.com, and we'll get your questions on the show. Okay, so we had some questions related to surface plates. Why don't we throw up the first one there? What is the easiest way to perform a legitimate, complete test on a smaller surface plate? Surface plates come in a lot of different sizes, right? And I'm guessing he's talking about these little...
They go from 12 to 18 inch up to 20 by 30 feet.
Right.
You always hear stories about back in the Midwest where, automotive manufacturing, airplane, aerospace manufacturing, just huge, 20, 30 feet long.
So we're talking about something that's the size of a sheet of paper.
Sheet of paper,
Okay.
yeah. So the smaller surface plates, a surface plate has to have two different checks made to it, regardless of size. Flatness and repeatability. We've covered this on our different gauging qualities on calibrating a surface plate, but those two checks have to be made. His question was, he was using a laser system, and a laser system is accurate, but it has a lot of hardware. You have the laser going through an optic, and then you have a target that moves along a straight edge, and you have reflecting mirrors on the corners, and it's a lot of hardware. On a 12 by 18 inch, you'd almost be brimful of hardware. You wouldn't have any room to move.
You have 3 inches in the middle that you can actually measure. Yeah.
So I can understand his concern. Really, I've got a response for that. What I think would be something that would work, and it would be affordable, and it would be portable, would be the old planicator system. Planicator was originally made by Rahn, R-A-H-N. I believe now TrueStone handles it. But they are a slab of a reference straight edge. They call it a reference granite straight edge.
Okay.
That sits up on two different supports, and you run an indicator, a very accurate indicator underneath it, usually a MAR indicator, which is graduated in 10, 20, about 20 millions. I think they're 20 millions per division.
So so what in between the
bottom
of the bottom of the planicator and the top of the surface plate?
Right.
Okay.
Right. The planicator is above, and the indicator goes between the two. The top surface is perfectly level, so it should always measure 0. What you're going to see in deviation is the surface plate.
Now, would the planicator rest on...
Two stands.
But on top of your surface plate, or would you put that on top of a bigger surface plate and kind of bridge over the top?
The planicator sits right on your surface plate, and there's a method for leveling your planicator to the plate. Okay.
And they make them small enough
They make them 24-inch, which I had one forever. Okay. And you could carry it anywhere. You don't need power, electricity. It's a stone with an indicator, so it's very portable. They're very accurate, and they are acceptable for use. There are more accurate methods, but when you're working with a 12 by 18 inch or a 12 by 12 inch, real estate on the plate is at a premium. This would work. This would be a great, I would suggest a planicator. There are other methods, but that seems to me to be the best choice for this situation. It wouldn't be accurate enough probably to use on a grade AA, a lab grade plate. Now you might have uncertainties that aren't keeping in the 4-to-1 ratio. But on a grade A, or especially a grade B, a tool room type of plate, it would be perfect.
Okay. Another question. Next question. Is the MAR Federal Electronic Leveling System worth purchasing to accompany our laser system? Would it be useful for doing the smaller surface plates? It doesn't seem like using the electronic leveling system is an option for smaller surface plates. Now, is the MAR electronic leveling system, is that what we had in here a long time ago when we were measuring this surface plate?
Yes.
Okay.
They're about 4 inches long. There's two levels, 4 inches long. They sit side by side. One of them, you zero them to the plate, and then one of them moves. And so you're dealing with less hardware than the laser. It's not an inexpensive system. It's a great system. I love it. It's not cheap. I don't know if I could rightly suggest supplementing your laser with it. It may do one or two plates that it may do plates a little smaller than your level can fit all that hardware on, then your laser can fit all that hardware on. It's a very accurate.
But even these are fairly, you couldn't use on a very small, they're 4 inches, pretty big,
On a 12 by 12, you're ending up making two inch movements,
and actually
but it'll do it.
You have to go in from the edges a little bit too.
You do have to, and the viewer was concerned about the edges. The edge roll-off is going to be regardless of the system you use, it's going to come into play. It's just the larger your hardware to measure it, the worse it becomes. depending on the width of what you're dealing with.
Okay.
So I don't know if that would be, if you have the budget for it, be great, you're going to love it. But just to supplement it, I don't think it'll allow you to do too many more plates. And I agree with the viewer that still might not be the best method for the very small plates.
Okay. And actually related to small plates, we have one other question on that. Same viewer. I have seen several small surface plates, perhaps 9 by 9, associated with particular indicators. These very small plates are not covered under the ASME D893.3.7 2013 spec. Can a calibration be performed on these?
Well, yes it can. These typically are not surface plates. These are typically called drop indicator bases or indicator bases. Don't know if I like using the word drop with tools.
In a calibration lab, drop always seems like a scary word.
These are indicator bases, and they're granite. They're not specified as tight as surface plates. Typically, they're in the range of, their flatness should be 1/10,000th of an inch to 5/10,000ths of an inch. So 1/10 to 1/1000th. And that can be, you can check it a different way. You still could use the planicator, but now you're talking really small. You're talking 9 by 9, 6 by 6 inch, 4 by 4 inch. But with a tolerance like that, what we would do is we'd start off with our lab grade surface plate, and the person doing this probably has a lab grade plate by what I'm seeing with their other equipment. You start off on your lab grade surface plate, you'd put a leveling device. We use a leveling plate. You could use 3 jack screws. You'd put that indicator base on top and level the top surface. You're just leveling it to 3 points. And then you'd sweep it with a very accurate indicator and look at the variation. What we use is a leveling plate, and I have an auto ranging indicator, which starts out with a very broad resolution, and it just, as it gets better, it hones in. So I can get a 3-point level very accurately, and the finest resolution on that's 5/millionths of an inch. I can get it level quickly and very accurate.
So I'm trying to visualize. Can we go to the gauge cam here?
We can try to draw one here. All right, hold on a sec.
Okay,
so what we're going to have
you have your
is our surface plate.
Okay, there's your surface plate.
And then I'm going to put my leveling plate on it.
Okay, and level that out.
Draw this out because it's going to take just a minute here.
Okay.
Now you'll know why I'm a calibration owner, not an artist. These are leveling knobs, and I believe this is a fixed reference. So we will set their base. How am I going to draw this? Their base is going to set on here, and that's the pole that holds the indicator. It's going to set on there, and we're going to level it to 3 points.
Okay, so you've got your leveling plate on top of your surface plate.
And theirs on top of it.
That on top of that, and then you have your indicator that you just sweep across.
Our indicator is going to ride on our plate, and we're going to approach it from different angles.
Okay.
And once we've leveled it to 3 points, now we can use our indicator, and that'll tell you very easily, are you within the 1/10,000ths to 5/10,000ths.
Now, I would think that there's going to be some, speaking of measurement uncertainty, some tolerance stack up. I mean, you've got the tolerance of your surface plate, and then you've got tolerance of the flatness of this.
You wouldn't have this because you're leveling it to 3 points.
Oh, okay.
The only tolerance you are going to be dealing with is the lab grade plate and the tolerance of your indicator.
And the indicator itself. Okay. Okay.
So it's pretty insignificant when you're dealing with 0.5.
Yeah, the surface plate. Yeah.
You're resolving to 5/millionths. It's pretty insignificant. That would be an appropriate method to check the smaller ones. That's how we check them when we get in those indicator bases, and we can even bring that. We can bring their indicator base in and do them quite rapidly.
Many people have these leveling.
The leveling plates. I don't know how many people have them.
Are they expensive or?
Oh, $300 or $400, maybe more.
Okay, so not bad. I mean.
And Starrett makes jack screws, which would do the same purpose.
Okay.
If you've ever seen those, they expand outward. They have a little rod through them that you can twist.
Okay, yeah, sure.
So
sure.
It's all about getting 3 points level on the top of what you're checking quickly.
Okay.
That's the whole point. Can you get it accurate and quick?
Okay.
Because they're not expensive devices, you can't spend all day doing it.
All right. Why couldn't you just set this small surface plate directly on top of your surface plate and measure it?
They may not be level to each other. Typically, the indicator bases will have rubber pads, rubber feet on the bottom.
Okay.
Sometimes they'll be missing a foot.
Okay.
It might be 2. Sometimes they'll have 1 foot.
Okay. Oh, so when you said level, you meant
Level to the plate.
So I mean, you put the small surface plate on top of the leveling plate and then level it.
Right.
You level the top of your surface plate that you're measuring.
Right.
Got it.
The leveling plate just goes in between like a sandwich.
Okay. Got it. Okay.
So that is how we do them, and I would suggest that might be a good way to do the smaller plates.
Okay. We did have another question that just came in a few minutes ago. By the way, just a reminder, if you got any questions, send them to techno-live@qualitydigest.com. You mentioned the rule of thumb of 4:1 for calibration standards, and that it has recently been revised. I'm not sure you said that. The question is, what has it been revised to, and what standards is this rule available in?
All right, I think we got an answer for that.
Okay.
ISO 17025, 10112, they will address the old 4:1 ratio. They will say you must provide measurement uncertainty, or TUV, or some form of that. They'll say, we don't care if you want to refer to the old 4:1, you're welcome to.
Okay.
But that's not enough anymore. So they have revised it to that's not enough anymore. You need to provide a measurement uncertainty.
Oh, so, okay, so what they're saying is not that it has to be tighter than 4:1.
Correct.
They just want an actual number.
They want it defined.
They want it defined. Okay. So it could be 3:1, it could be 10:1, but
as long as everybody's on board.
everybody's
yes.
on board. Okay. All right.
So that's a good question, and it's probably mentioned. I don't know in the family of the ISO 9000 certs if they mention that. They might not get into that level. They might, but I know it's become where that isn't enough. That used to be the standard default blanket we would work to make sure we are 4:1 or better. A lot of engineers will say 10:1. So they keep it in that range, but now it is as specified. You need to provide an uncertainty.
Okay. Christopher, were there any more questions? That's it? Okay. So let's take another couple of minutes just in case some last minute questions come in. Remember, any questions right now you have, techno-live@qualitydigest.com. You know, we've talked a lot about surface plates. I just want to touch bases on a little bit more just because, number one, we have a great, one of the first gauging qualities we did was actually the calibration of a surface plate. It happens to be the surface plate we have here in the studio. Really good. This thing's been viewed thousands of times because Craig did a really awesome job of showing how we calibrated that surface plate using the MAR electronic leveling system.
Correct.
I mean, I guess it's worth reiterating that the surface plate for most of the measurements that you do in a calibration lab, whether it's an outsourced calibration lab or in-house, it's basically literally the bedrock for everything that you do. I mean, it's important that it is calibrated and kept clean. And I mean, just feel as I think it's worth repeating.
I'd agree with that. That's the basis of your measurement. The surface plate, your gauge blocks, all your standards are important, but the surface plate is what everything's going to sit on. You know, if you're using it as a reference, it has to be accurate. Your measurements are only going to be as accurate as your weakest link.
Right.
And you sure don't want the surface plate to be the weakest link. Some people view it a little different. They'll say it's granite. Come on, it's a rock. How bad can it be? It's got to be flat. They wear quite a bit. Resurfacing is a common activity for the surface plate companies. They will resurface it to different grades.
And by the way, we showed in that same video that it doesn't take much of a smudge on the surface plate to really throw. I mean, something thinner than a piece of paper. I mean, a stain from where a Coke has etched away part of the. I mean, all sorts of things. I mean, it doesn't take much to throw off a measurement if you happen to set your indicator, whatever, on top of that damaged part of your surface plate. You're going to get a wrong measurement.
That's correct. One other thing I might want to mention, that we were talking about the data earlier on the calibration certs, that some companies show them, some companies don't. Something you, the customer, should know. It's required by the ISO programs, and it's just common sense, that we, the calibration lab, take data. Regardless of if we report it to you or not, it's required that we take and we store that data to objectively show your tool was good. Give you an example. Let's say a micrometer, and you've opted not to have data provided, you just want a pass or fail. We'll provide you with the cert that says pass if that's what you're requesting, but an auditor can come to us and say, I need you to objectively show me, what did you check on that micrometer? You can't just say, well, it passed everything, it was good. We need to show we checked flatness, we checked parallelism, we checked lead error, did we notice anything, things like that. So by the way, a competent calibration lab will have the data stored. It has to be, because we may be questioned, this part you say is, this tool you say is good, but there's an issue out there. There was some sort of a problem. We have to objectively be able to show that what we did checked all the different parameters.
Right. Okay, Christopher, any more questions? Nope, that's it. Okay, well, that actually wraps up our show for today. Very informative. Thanks a lot. A lot of good information there on calibration certificates and what you should be looking for. Some of the things that, as you mentioned, are required, and some that are just kind of good practice. If you're gonna outsource your calibration, if you don't do it in-house, well, actually, I would say two things. If you're doing it in-house, you probably want to do everything that Craig just mentioned, even if it's done in-house. And if you're outsourcing, you might want to make sure that the calibration lab that you're using is doing those things that Craig's mentioning. It helps reduce your risk, gives you more information into the process that they're using when they calibrate your tools. So that's all good stuff. Craig, thanks a lot. I appreciate that. So that wraps up our show today. Our thanks to our sponsor, PQ Systems. For more than 30 years, PQ Systems has provided solutions to help organizations implement quality improvement programs and demonstrate proof of their quality performance. We mentioned actually their product in the show. Visit www.pqsystems.com to see the full range of products and services that PQ System offers. Craig, once again, thanks for joining us, and we will see you all again at the next Gauging Quality. So long.
Thank you very much.
Three, two, one, fire.